Modern AI workloads generate extreme, concentrated thermal loads. At scale, a high-density cluster requires the continuous removal of up to 11.35 megawatts of heat. If that thermal energy isn't extracted instantly, the processors will thermally throttle. To solve this, engineers rely on a strict heat split rule. The total IT load, plus any ancillary equipment heat, must be divided into two removal paths: liquid capture directly at the chip and residual air capture in the room. This schematic outlines three isolated loops: the blue and red facility water system, the cyan and orange technology cooling system, and residual air. Routing liquid directly to the racks extracts 80% of heat at the silicon, leaving 20% for room air handlers. Pumping legacy single-loop chilled water directly onto the server floor is impossible at this density. You have to establish absolute physical isolation between the raw, high-pressure facility water and the delicate silicon processing cores. Looking at these architectures, the right shows a conventional chiller. The middle illustrates our target: a StatePoint plant, coolant distribution unit, and direct-to-chip plates. The CDU acts as a hydraulic firewall, segregating high-pressure exterior water from the microfiltered technology cooling system. Within this boundary, 42 degrees Celsius return fluid from the servers meets 28 degrees Celsius facility water supply. This achieves a highly efficient 4 Kelvin approach temperature, transferring massive amounts of heat without a single drop of fluid ever mixing. This transfer occurs across plate heat exchangers. These plates completely block exterior water chemistry, pressure excursions, and raw contaminants from reaching the data hall. The CDU is a control barrier. By mathematically regulating differential pressure, fluid purity, and approach temperatures, it isolates and protects the entire IT payload from external faults. Down at the server level, direct-to-chip cold plates pull heat off the processors. To remove 70 kilowatts of heat from a single rack, the system pushes a precise flow rate of 74 liters per minute across the server manifold. The internal fluid loop adheres to strict material constraints. It requires marine-grade 316 stainless steel, with zero brazed copper, zinc, or brass permitted anywhere in the fluid path. These restrictions eliminate galvanic corrosion. If lesser metals were used, copper ions could migrate through the coolant and deposit directly onto the server logic boards, causing systemic component failure. The CDU also executes precise dew point control. It maintains a 32 degrees Celsius liquid supply temperature against a typical 23-degree room dew point, locking in a strict 9 Kelvin safety margin. That 9 Kelvin margin prevents localized frame sweating. It ensures no condensation drops onto the surrounding air-cooled legacy infrastructure running in the same hall. Inside the CDU modules, fluid distribution relies on true N+1 active-active variable speed pumps. If one pump fails, the others automatically ramp up to maintain exact loop pressure without interruption. Fluid quality is heavily guarded. Full-flow 50-micron filters protect the fine fin pitches inside the cold plates, while integrated microbubble air separators absorb the rapid fluid expansion that occurs when GPUs spike to full load. The electrical demands are equally controlled. The pumps use active front-end variable frequency drives to keep total harmonic distortion under 5% at all loads, preventing high-frequency feedback from disrupting the emergency generator buses. The unit's programmable logic controllers, human-machine interface, and at least one primary pump drive are wired into a continuous DC-ORed UPS buffer, guaranteeing a sub-20 millisecond power write-through during utility transfer gaps. High-density AI chips will hit their thermal limits and throttle within 5 to 10 seconds of flow loss. That sub-20 millisecond mechanical response is a mandatory requirement for achieving uptime Tier 4 continuous cooling compliance. This diagram outlines the exterior heat rejection layer. The roof-mounted StatePoint plant absorbs the building's thermal load, sending 28-degree facility water supply down to the CDUs and receiving mixed return water at roughly 38 degrees. Inside the StatePoint unit, heat is rejected without using standard refrigerant cycles. Warm water is distributed across this middle layer, passing through a highly specialized membrane array while fans pull scavenger air upwards. The system utilizes tri-mode automated staging. It dynamically shifts between dry, adiabatic, and membrane evaporative cooling based on ambient weather, actively balancing fan power against water consumption to optimize efficiency year-round. This cross-section shows the sub-micron physics at play. Recirculating water forms a thin film on the hydrophobic membrane. Only water vapor diffuses through the microscopic pores into the moving air. while liquid water and dissolved solids remain sealed inside. By locking the loop's hydrostatic pressure below the membrane's liquid entry pressure, under 1.5 bar, the architecture physically blocks raw outside air, eliminating the risk of launching aerosolized biological pathogens into the atmosphere. System resilience extends to predictive software logic. The plant's programmable logic controllers cross-reference live weather feeds, executing dew-point look-ahead tuning to adjust cooling modes 15 minutes before a high-humidity weather wall arrives. By reacting before the air actually changes, this pre-modulation prevents the fans and pumps from oscillating or hunting for a set point during sudden monsoon or tropical rain spikes. At the sub-micron level, the system manages extreme, instantaneous computing surges through dynamic fluid velocity boundary sharing. When AI workloads hit maximum utilization, the control logic rapidly modulates the secondary water velocity. This physical sharing action continuously breaks up stagnant air and fluid boundary layers across the membrane face. Static cooling curves cannot handle instant thermal spikes. Without high-velocity boundary sharing, localized heat pockets will choke the membrane's capacity, causing rapid thermal stagnation. Let's examine the deterministic fault matrix. In the event of a primary pump trip, the system detects the flow decay. The standby pump engages instantly to maintain flow above 271 liters per second, preserving full cooling capacity. If a catastrophic chip-side fluid line breaches, the CDU utilizes negative loop pressure management. Instead of spraying liquid out onto the electronics, it pulls a vacuum and draws ambient air inward. Simultaneously, optical drip pan sensors alert the leak sentry matrix. Motorized isolation valves shut down the local loop feed in under 10 seconds, preventing a multi-rack fluid loss. During a complete utility power loss, the mechanical design takes over. Thermal buffer tanks holding 120 cubic meters of fluid provide exactly 90 seconds of full load ride-through capacity, bridging the critical gap while backup generators synchronize. To handle long-term maintenance, the plant utilizes automated in-situ clean-in-place technology. It executes low-pH organic acid flushes that dissolve calcium scale while the unit is still live, meaning a membrane cell can be rejuvenated without dropping site cooling capacity. Steady, authoritative. Achieving continuous cooling for high-density continuum requires deterministic, automated physics that isolate faults in milliseconds, protecting the facility without ever dropping the AI workload.